The engineering irony is brutal. SpaceX built Mechazilla specifically to avoid heavy landing legs. Now the moon demands the biggest ones they've ever designed. Here's the hard reality. Recent American lunar landers, like Odysseus, keep falling over. The moon's 1/6 gravity makes tall structures dangerously unstable. Physics shows landing legs need to be 2.5 times wider on the moon than Earth to prevent tipping. For Starship's 50-meter height, that means massive, expensive legs used exactly once. The same weight problem Mechazilla solved on Earth becomes exponentially worse on the moon. SpaceX faces three brutal options: build enormous disposable legs, attempt risky horizontal landings, or construct lunar infrastructure that's years away. With Artemis 3 targeting 2027, time is running out. The decision will define humanity's lunar future and SpaceX's engineering legacy. Let's dive right in. During a SpaceX Flight 10 webcast, company spokesman Dan Witt made a casual comment that revealed everything. When discussing Mars landings, he said, "They're just going to put minimally viable landers on the surface. Land right on the skirt, no landing legs." This single statement exposes the massive contradiction SpaceX faces. If they can land on Mars without legs, why does the moon demand the biggest, heaviest landing system they've ever built? The answer lies in physics that most people completely misunderstand. SpaceX didn't build Mechazilla for fun. They built it because Starship became too heavy for traditional landing legs. At 50 meters tall and over 100 tons empty weight, Starship dwarfs the Falcon 9 that successfully uses retractable legs. The math is brutal. Engineers estimate Starship would need at least 6 massive legs made from carbon fiber with aluminum honeycomb cores. On Falcon 9, these expensive materials make economic sense because the rocket flies repeatedly. Each reuse justifies the high upfront cost. But Starship's lunar version breaks this equation completely. The human landing system has no heat shields, no re-entry flaps, and no return capability. It's designed for one-way trips to the moon's surface. Those expensive carbon fiber legs become the most costly lunar decoration in history, used once and abandoned forever. This economic reality drove SpaceX to develop Mechazilla's catch system, but the solution that works perfectly on Earth becomes impossible to replicate on the moon, creating the engineering trap SpaceX now faces. February 2024 delivered a harsh lesson about lunar landing reality. Odysseus, built by intuitive machines, became the first American spacecraft to reach the moon in over 50 years. The mission should have been a triumph. Instead, it became a warning. Odysseus toppled over during landing. At just 14 feet tall, the lander couldn't maintain stability on the lunar surface. Its antennas pointed sideways instead of toward Earth. Solar panels faced the wrong direction, and mission capabilities were severely compromised. The failure pattern repeated in 2025 when Athena, another intuitive machines lander, also fell sideways during touchdown. 2 consecutive American lunar missions, 2 sideways crashes. The message became clear. Even small landers struggle with lunar stability. These failures weren't flukes or bad luck. They revealed fundamental physics challenges that affect any tall, narrow vehicle attempting to land on the moon. And Starship is nearly 4 times taller than Odysseus. Most people assume the moon's weak gravity makes landing easier. This assumption is dangerously wrong. The moon's gravity is only 1/6 of Earth's, and this creates stability problems that don't exist on our planet. Dr. Sarah Chen, a former NASA flight dynamics engineer, explains the counterintuitive reality. On Earth, gravity helps keep tall objects upright by pulling their center of mass downward. On the moon, there's barely any downward force to resist tipping motion. Think about those Apollo astronauts bouncing around and occasionally tumbling during moonwalks. They weren't just having fun. They were demonstrating how easily things fall over in weak gravity. An astronaut weighs about 60 pounds on the moon instead of 360 pounds on Earth. That missing weight eliminates the natural stability we take for granted. This physics principle scales up dramatically with larger objects. A 50-meter rocket has enormous leverage working against it. Any sideways motion during landing gets amplified by the vehicle's height, and lunar gravity provides minimal resistance to tipping. The engineering analysis reveals the most disturbing number in this entire story. Landing legs must be 2.5 times wider on the moon than on Earth to handle identical sideways velocities during touchdown. Let's translate this into real dimensions. If Starship needs a 6-meter leg span on Earth, the lunar version requires 15 meters of spread. That means legs extending nearly 25 feet from the rocket's center line, wider than most residential streets. But width is just the beginning of the engineering nightmare. These aren't simple telescoping struts like on smaller rockets. Each leg must support concentrated loads at specific attachment points, while the cylindrical vehicle experiences bending stresses it was never designed to handle. The structural requirements multiply the weight penalty exponentially. Stronger attachment points, reinforced mounting brackets, and massive leg structures all add mass that reduces payload capacity and increases mission cost. SpaceX's propellant choice creates an additional complication that makes the height problem worse. Starship burns liquid methane and liquid oxygen, but methane weighs roughly twice as much as oxygen. If engineers placed these tanks side by side, the rocket would be unbalanced and impossible to control. The only solution is stacking the tanks vertically, which makes Starship taller and more unstable during landing. This creates a vicious engineering cycle. The fuel choice demands vertical stacking, which increases height, which requires bigger legs, which add weight, which demands more fuel capacity, which makes the rocket even taller. Every design decision compounds the stability problem. The tank configuration that works perfectly for orbital flight becomes a liability during lunar landing operations. The Odysseus mission revealed another terrifying vulnerability that could affect any lunar lander. During final descent, the spacecraft's laser altimeters malfunctioned, leaving it blind to altitude and descent rate. Without accurate altitude readings, Odysseus hit the lunar surface much faster than planned on a 12-degree slope that exceeded its design limits. The impact immediately broke one of its 6 legs. With compromised landing gear, tipping became inevitable. The failure cascade demonstrates how quickly lunar landings can go wrong. Starship relies on even more complex systems. Computer vision, radar altimeters, and navigation computers all working perfectly during the crucial final seconds. Any single failure could replicate Odysseus's fate, but with astronauts aboard instead of just scientific instruments. Faced with impossible vertical landing constraints, some SpaceX engineers have quietly explored a revolutionary alternative: landing Starship on its side instead of upright. The concept sounds crazy until you examine the physics benefits. A horizontal Starship has a dramatically lower center of gravity and much wider ground contact area. Tipping becomes nearly impossible because the vehicle is already lying down. Astronaut access improves dramatically. Instead of complex elevator systems to reach a vertical cabin 50 meters above ground, crew members could enter directly at surface level. Cargo unloading becomes simple instead of requiring elaborate crane systems. The engineering challenges, however, are staggering. Spacecraft structures are designed for axial loads along their length, not lateral forces across their diameter. The circular cross-section that handles vertical thrust beautifully becomes a structural weakness when loaded from the side. Every internal system would need redesign. Fuel systems, life support, crew quarters, and cargo bays all assume vertical orientation. Converting to horizontal operations would require fundamental changes to the entire vehicle architecture. Horizontal landing creates an even bigger challenge. How does the spacecraft leave the moon? The main Raptor engines point along the vehicle's center line. In a horizontal configuration, these engines aim sideways instead of up, making them useless for vertical ascent. SpaceX would need entirely separate propulsion systems for takeoff, or complex mechanisms to reorient the entire vehicle before departure. Both solutions add massive weight penalties and multiple new failure points to an already complex system. The fuel management nightmare gets worse in horizontal position. Liquid propellants slosh freely in sideways tanks, shifting the center of mass unpredictably during engine startup. Imagine trying to balance while carrying a half-full water balloon. Now scale that to hundreds of tons of cryogenic fuel. Elon Musk's long-term vision includes building launch infrastructure on other worlds. A lunar Mechazilla could theoretically catch Starship just like on Earth, eliminating landing legs entirely. The technical challenges make this approach currently impossible. Mechazilla stands over 140 meters tall and weighs thousands of tons. Every component would need transportation to the moon or manufacturing from local materials using technologies that don't exist yet. The precision required to catch a descending spacecraft becomes exponentially harder in lunar gravity. On Earth, Mechazilla's massive structure provides stability. On the moon, the same tower would be much lighter and potentially unstable itself. Current lunar construction capabilities couldn't build a simple shelter, let alone a rocket-catching skyscraper. The industrial infrastructure required for Mechazilla construction is decades away from reality. NASA's Artemis 3 mission targets 2027 for the first crewed lunar landing in over 50 years. This timeline gives SpaceX less than 3 years to solve problems that have stumped aerospace engineers for decades. The company faces 3 realistic options, each with severe drawbacks. Massive disposable legs violate SpaceX's efficiency principles but offer the highest probability of mission success. The weight penalties reduce payload capacity and increase costs. But proven engineering approaches minimize risk. Horizontal landing could revolutionize lunar operations if successful, but represents an enormous technical gamble with astronaut lives at stake. The engineering challenges require solutions that don't currently exist. Mission delay until lunar infrastructure development becomes politically unacceptable as international competitors advance their own lunar programs. The timeline pressure eliminates the luxury of extended research and development cycles that characterize the Apollo program. While SpaceX wrestles with Starship's landing challenges, China's space program advances steadily using smaller, conventional landers that avoid these scale problems entirely. Their approach may be less ambitious, but it sidesteps the engineering nightmares that plague larger vehicles. If SpaceX delays too long solving their technical challenges, China could establish permanent lunar presence first, fundamentally altering the geopolitical landscape of space exploration. This competition adds political pressure to every engineering decision. The technical solution SpaceX chooses will determine not just mission success, but American leadership in space exploration for decades to come. The lunar landing approach will directly impact Mars colonization plans. Mars has 38% of Earth's gravity compared to the Moon's 16%, which reduces stability problems significantly, but doesn't eliminate them entirely. If SpaceX develops massive landing legs for the Moon, those systems could adapt for Mars use with modifications. The engineering investment pays dividends across multiple worlds. Alternatively, successful horizontal landing could revolutionize Mars operations completely. Imagine Mars colonies built around horizontally landed starships, serving as ready-made habitation modules, with easy ground-level access and cargo handling. The Moon mission isn't just about returning to Earth's satellite. It's the testing ground for technologies that will enable human expansion throughout the solar system. NASA's safety requirements add final complexity to every design decision. The agency learned painful lessons from space shuttle disasters and accepts no shortcuts when human lives are at stake. This regulatory reality favors conservative engineering solutions over innovative approaches. Massive conventional legs may be boring and expensive, but they're easier to certify than revolutionary horizontal landing systems. SpaceX's culture of rapid innovation clashes with NASA's methodical, risk-averse approach. The final landing system will reflect whichever philosophy wins this internal battle between breakthrough technology and proven safety. The decision made in the next few months will echo through decades of space exploration, determining whether humanity reaches for revolutionary solutions or accepts conventional limitations. Either choice will define SpaceX's legacy and humanity's future beyond Earth. This is exactly why SpaceX built Mechazilla in the first place, to escape the tyranny of landing legs. But the Moon's brutal physics has forced them into the one scenario they spent billions trying to avoid: designing the most massive, complex landing system in aerospace history. What this means is that sometimes the most advanced engineering solutions create entirely new problems. SpaceX revolutionized Earth landings by eliminating legs, only to discover that lunar missions might demand legs bigger than anyone imagined possible. The irony runs deeper than engineering. It reveals how each world in our solar system will demand completely different approaches to human exploration. There's no universal solution, only adaptive innovation. This landing challenge represents more than just SpaceX's engineering dilemma. It's the first major test of whether private companies can solve problems that stumped government space agencies for decades. The solution they choose will define the template for all future planetary exploration. Every engineering decision made for Artemis 3 becomes the foundation for Mars colonies, asteroid mining, and expansion throughout the solar system. We're not just watching SpaceX solve a landing problem, we're witnessing the birth of multi-planetary engineering principles. The stakes couldn't be higher. Success here doesn't just return humans to the moon, it proves that breakthrough thinking can overcome physics challenges that seem impossible. SpaceX has until early 2025 to finalize their landing system design for Artemis 3. The next 6 months will reveal whether they choose massive conventional legs, attempt revolutionary horizontal landing, or develop some hybrid approach nobody has considered yet. And this is just the beginning. Whatever solution emerges for the moon will immediately face scaling challenges for Mars missions. The engineering principles proven on lunar missions will determine how quickly humans can establish permanent presence on other worlds. The space industry is watching every decision because SpaceX's choice will influence landing system development for the next decade of planetary exploration missions. But here's what I want to know from you. Do you think SpaceX should stick with proven engineering and accept massive landing legs, or take the revolutionary risk of horizontal landing that could change everything? The engineering is complex, but the philosophy behind the choice will shape humanity's space future. What approach would you bet on for getting humans safely to the moon and back? Let me know in the comments, because this decision affects all of us who dream of becoming a multiplanetary species. This is Space Hub, and we dive deep into the engineering challenges that will define humanity's expansion beyond Earth. If you want more analysis on how breakthrough technology solves impossible problems, hit subscribe for the latest developments in space exploration. For the most detailed coverage of SpaceX's final landing system decision and its implications for Mars missions, you know where to find us. The Moon Landing Challenge isn't just about returning to our nearest neighbor. It's about proving that human ingenuity can adapt to any world we choose to call home.